machine learning and artificial intelligence. Technology is influencing the way we do things, and metaphysics of artificial intelligence is advancing significantly, projecting a new paradigm in developing new cognitive machine learning intelligent Neural-Morphic platforms. With research and development centers in Miami and Medellin, the mission is to provide solutions by applying our technology offerings to product development, with emphasis in medical pulmonary ventilator systems, such as the engineering prototype illustrated in this video. The need for smart ventilators is evident. Patients with COVID-19 present symptoms from lack of oxygen in their lung capacity. The best medical treatment is to assist the lung function with the electromechanical ventilation system. The BVM is a plastic balloon or plastic bag that can be manually compressed without having to perform mouth-to-mouth resuscitation. It is an easy and simple way to force air into the lungs. The challenge is how to manage the supply of oxygen into the patient's lung and managing the side effects caused by the electromechanical ventilation system, such as barotrauma. Alveoli allows to diffuse the blood in the lungs. They are tiny air sacs in the lungs that are in contact with the blood vessels to allow oxygen and carbon dioxide to diffuse between the blood and the lungs. These are very delicate pieces of tissue. Overexpanding them will lead into inflammation. This is what is also known as barotrauma. The spirometer is an important feature to measure the airflow rate out of the BVM, to calculate the amount and volume of air delivered, typically 200 milliliters of volume up to 750 milliliters. Here the smart microcontroller can measure and control the volume and the pressure parameters. The time-based frequency of the system ranging from 5 to 30 breaths per minute. This is the mandatory breath. At this point, the patient must be heavily sedated. The machine needs to trigger the breath cycles and ending the breath cycle as well. The embedded CPU will detect and control the breath trigger and timing. There are a multitude of other design parameters and considerations that need to be taken into perspective. The Neural-Morphic embedded microprocessor allows the implementation of sophisticated signal processing of the measurements provided by sensors, leading not only to a better measurement accuracy and better rejection of noise and artifacts. It also deals with the generation of new information by appropriately computing and integrating several variables. These variables expanded information that can be used by the ventilator to optimize the ventilation parameters. The ventilator paradigm is controlled by a sophisticated Neural-Morphic embedded system to allow exact adaptation of pressure and flow characteristics. Fine-tuned ventilator settings also serve to make ventilation more tolerable and comfortable. The artificial intelligence microprocessor pressure ventilator consists of a compressible air reservoir, air and oxygen supplies, a set of valves and tubes, and a disposable patient circuit. The air reservoir is pneumatically compressed several times a minute to deliver room air and air-oxygen mixture to the patient. The ventilator with a flow valve adjusting pressure to meet patient-specific parameters. When overpressure is released, the patient will exhale passively due to the lungs' elasticity. The exhausted air being released usually through a one-way valve within the patient circuit called the patient manifold. The software platform consists of complex mathematical algorithms and sophisticated software models. Many of these models are developed with Python and C++. The main objective is to provide the control environment for the motor and sensory segments. Here, I will illustrate an engineering alpha test model of the proposed ventilator system. Non-invasive methods such as continuous passive airways pressure and non-invasive ventilation, which are adequate for patients who require ventilator only while sleeping and resting, mainly employ the nasal mask.